Hey Algebra 1 students, we're still in Chapter 1 and we are checking out Section 5, Equations and Functions. As usual, we're going to start off with our vocabulary words, and I have to admit these are kind of heavy. There's a lot. So do pay attention. I'm going to try to chunk them in a way that's going to make sense, and hopefully you can see the relationships between them. So here's our vocabulary list, and let's get started. Our first couple of terms I think go together well. The overarching term here is an open sentence. An open sentence in math is a math sentence that has an equal sign or even an inequality sign. This one being greater than or equal to, less than or equal to, less than, and of course simply not equal. And it has to have at least one variable. So an example of an open sentence would be like 3 plus r is equal to 7. It's considered an open sentence because it is open in a sense to whether it's true or not, depending on whether or not we get the right answer for r. So if I were to put a 2 in here, that would not work because 3 plus 2 is not 7. But obviously if I were to put a 4 in here, that works. So it's considered open because of that variable. It is an open sentence. And equations, as you know, would simply be a number sentence containing an equal sign. So if there's an equal sign, 3 is equal to 4 minus t. This is an equation. So oftentimes equations are open sentences, but all open sentences aren't equations. So the definition of solving is to find a value for a variable that's going to make an open sentence true. And as I think we were doing in the last example, if I have 3 plus r is equal to 7, the act of actually finding the value for r is what solving is about. And I think you guys probably knew that. In solution, we take the same example, 3 plus r is equal to 7. We know that r must equal 4. That is considered the solution, the replacement value of a variable that makes the sentence true. Obviously, if it doesn't make the sentence true, it's not a solution. In mathematics, we often talk about sets of things, sets of numbers. I can think of the set of all even numbers, or the set of all odd numbers, or the set of all negative numbers, or the set of all numbers in general. An element is a member of the set. So for instance, let's say I limited my set to 1, 4, 8, and 10. Maybe this is the set of my favorite numbers. An element of that set would be 1, or 4, or 8, or 10. An element is just one member of a set. A solution set is the set of all elements from a replacement set that makes a sentence true. So if I were to consider a problem like this, 36 is equal to x squared. And I were to consider certain values from a set to be replacement sets. So I'd say you can try 1, 4, -6, 6, and you can try these numbers. So this is the replacement set. This is a set of numbers that I'm going to allow you to replace in here for x. And the solution set are the numbers that will work. Can you tell me what numbers that will work here? What numbers can I put in for x that would work? Yes, you got it. -6 and 6. So the solution set looks like this. A solution set, again, is just the numbers that work given a certain set of numbers that you're working from. A replacement set, which I probably should have defined before we did the last slide, a replacement set is the set of numbers from which a replacement for a variable may be chosen. This terminology is really specific to our text, and what they're doing in using this language is kind of gearing us up for the concept of domain and so forth and so on. But just as we described in the last problem, sometimes you'll be given a problem, let's say x plus 3 is equal to 9, and it'll say for you to choose, use numbers in the replacement set to see which one works. So you might get numbers 1, 2, 4, 6, 7, and you're supposed to try all of these. This will be the replacement set, the numbers that you're allowed to replace for x. Not really a big deal. And then we do talk about the concept of set. Set is just a group of numbers that are often written as curly brackets, but as I mentioned last time, I could refer to the set of all odd numbers. And I'm not going to write all of those in curly brackets. I can write out the words, the set of all odd numbers. Or sometimes you'll see mathematically like 1, 3, 5, 7, and then you'll see an ellipse to indicate, okay, continue on in that fashion. And again, that refers to the set of all odd numbers. So oftentimes there are curly brackets, but it doesn't have to be. This should be the last item of our vocabulary, and it's the word identity. And we've been using that word around, throwing it around when we're talking about properties, but an identity specifically in math refers to an equation that is true for every value of the variable. For instance, this is going to seem really basic, but if I told you x plus 3 is equal to x plus 3, yup, that's true for anything. I could throw any number in there and that would work. So if I ever got to a stage in solving a problem and I saw this, I would know that this is an identity, and more specifically that the answer is any number, or any number will work there. And basically, just like it looks like an identity is like looking in the mirror. Oftentimes you see exactly the same thing on both sides of the equal sign. So this first example gives us a really good idea of how to use a replacement set. We're going to use a replacement set to find the solution set of the equation. So the equation is 2q plus 5 is equal to 13. We're going to use these numbers to replace into in this equation for the variable. A really good way to organize your information is to make a table like we've done down here. So if you notice that Q, the Q column has all of the possible values that I'm going to plug in for Q. And then I have the equation that I'm going to use it as a place to work things out. And then finally I have T or F, which is true or false. I'm going to change the way this 13 looks. It looks kind of, well, let me fix that whole thing. Okay, that's a little better. So what happens here is I'm going to just plug 2 right into the equation. Plus 5 is equal to 13, and I'm going to see if it's true or not. Is 2 times 2 plus 5 equal to 13? And it's false. It's not, because that's really 4 plus 5, which is 9. And I'm going to continue on down the list, checking to see which one works. So as we go down the list checking to see what works, we realize that the first one doesn't, nor does the second one. That's false. When I work out the what's on the left side of the equation, I get 11. And this next one, when I work out what's on the left side of the equation, I get 13. So that one works. I'm going to check all the other ones. But as we see, we get 15 does not equal to 13, so that doesn't work, and nor does 17 equal 13. So there's only one true value. So the solution set here is a set with one element, and that element is 4. Our next example has 2 parts, so definitely leave some space for parts A and B. Let's look at A first. Look at this equation. We've got a lot going on. What we want to do is simplify each side of the equation. Of course, we're going to use our order of operation rules. So the 7 is going to stay, but I'm going to deal with what's in the parentheses next by first dealing with the exponents, and then I'll deal with subtraction. So this becomes 16 minus 10 plus n is equal to 10. My next line will be 16 minus 10 is 6. So now the parentheses are gone. I've got 7 minus 6 plus n is equal to 10. Finally, 7 minus 6 is 1. Since everything here is subtraction and addition, I'm just going to go from left to right. 7 minus 6 is indeed 1. 1 plus n equals 10. So what plus 1 equals 10? Of course, that answer is 9. So n is equal to 9. So our solution is 9. Okay, so part B, we're going to do the same thing, simplify the left side and the right side as best we can, and then we're going to work on solving this. So n times the quantity of 3 plus 2. This looks like you want to go and use the distributive property, but it's unnecessary at this point because I can actually do what's in parentheses. So n times 5 plus 6 is what I now have on the left side. On the right side, I have 5n plus 10 minus 3 is 7. I'm going to rewrite this. 5n plus 6 is equal to 5n plus 7. I hope you feel uncomfortable with this because this is a very uncomfortable situation. There is no possible value of n, my n's look like h's, there's no possible value of n that's going to work here. And so when we come up with a situation like this actually is a no solution situation. There's no way this is going to work. There's no solution. And how can you tell? If we were to kind of continue on with the thought process, in a sense, since I've got the same thing on both sides, I can subtract them. And then I'm left with 6 equals 7. Really? Not at all. 6 does not equal 7. And therefore, in a situation like this, where it looks like both sides are exactly the same except something like this being off, what I know is that I used to tell students this is a lie. 6 does not equal 7. It's a lie. So when you end up with a lie, you know that there is no solution. And clearly these two things can't be equal. Another situation we could have, like we just had two situations where we got an answer for one and then we had a no solution situation for another. Another situation is where we can come up with an identity. So here we're going to see that identities happen sometimes when you are solving an equation. So let's do what we need to do. We're going to simplify each side. Let's start over here with the left side. 2 times 5 is 10. So this is 10 minus 8 times 3h plus 6. And that's all equal to all of this jazz over here. 2h plus, well, let me actually do that. 2h plus h is 3h. So this becomes 3h plus 6. And then I've got this 2 hanging outside here. And you know that's distributive property. So check it out. Over here, 10 minus 8 is 2 times 3h plus 6. And that's equal to, let's simplify this. I'm going to write it as 2 times 3h plus 6. Yeah, you see it. I just moved the 2 over here just so we can see that these are exactly the same. Even if I continue with the distributive property, I get 6h plus 12 is equal to 6h plus, looking in the mirror, 12. Same thing on both sides, my friends. This is an identity, same thing. So I know that everything works. All real solutions, all real numbers are going to work here. All real solutions. Solutions. All right. Okay, friends, you have been working hard. This is the last example. Example 4, we're going to deal with equations, or at least consider equations with two variables or two things that are not necessarily known. Mr. Hernandez pays $10 a month for movies delivered directly to his house by mail. He can rent movies at the store for $1.50 per title. Write and solve an equation to find the total amount Mr. Hernandez spends if he rents 3 movies from the store. I should probably add in a month. I think that might be more clearer. So in a month, we know that he's going to spend $10. And we also know that he is going to spend this amount, $1.50 per movie. So let M be the amount he spends total per month, right? So that be... All right, so M is the total amount spent per month, and V is the number of videos rented from the store, well, per month. So the relationship, the total cost, M, here's one variable, is really dependent on how many videos he rents from the store. So we know that we got that $10 fee all the time, but to add to that, we're going to add $1.50, right, times the number of videos that he rents. So this is the equation that we've created. And to use this equation, given a specific value, what was the value they gave us? They said write and solve an equation to find the total amount that Mr. Hernandez spends if he rents 3 movies in a particular month. So I'm going to circle that 3 so we can keep it in mind. He rents 3 movies, and I'm calling those movies videos. So I don't have 2 variables of M. So I'm going to plug that 3 right into that equation to solve and to get the answer that we're looking for. So we can see that M is equal to 10 plus $1.50 times 3. And then finally, we can conclude that the amount he spends per month is $14.50, recognizing that $1.50 times 3 is $4.50. And then we add the 10 on. All right, so here's our assignment. All right, so you guys are looking at pages 34 to 37, and the problems are as follows. Make sure you copy them down, circle them in your packet, makes it easier to do. Have an excellent, excellent day.